All right, so to finish up our dynamics and vibrations lectures, we're going to talk a little bit about vibrations. So you're going to encounter a lot of systems that are vibrating, and vibrations are essentially oscillating motions of a body or system from an initial position of equilibrium. Many types of vibrations. So you could think of, like, in your car, you have your shock systems with springs, and that system is vibrating, or it's kind of oscillating, moving back and forth and back and forth and back and forth. And one of the ways that we can model the motion of these systems is by considering, again, a model system. And one of them can be a fixed wall that's attached to a spring, and then we have a mass. So this is a classic spring mass system. If we were to analyze this system dynamically, so let's say, for example, we were to displace it from equilibrium and basically move it from this location to, let's say, this location. So we displaced it a little bit in this direction, x. So if it were displaced, or if the spring is elongated from its initial position, we have basically a force on our body where it is going to go back. So this is our spring restoring force. We can also look, so this is our direction for x. If we do our free body diagram, there's also going to be basically a weight here, a normal force here, which are going to cancel out. And we can also draw our kinetic body diagram. So we basically applied a force, and it's going to accelerate, or, basically, or if we compress the spring as well, that force will basically make it accelerate in this direction. So we applied some force in this direction, and it is accelerating. So we can go ahead and set up our system like this. So our kinetic body diagram, some of the force in the x direction, it's accelerating. The spring is wanting to pull it back effectively here. And we can see now that we have this expression. So we can use our relationship that we introduced way at the beginning of the class, that acceleration is the second derivative of x, or this x double dot. So we can rearrange our equation here from our forces to basically create what's called an ODE. This is an ordinary differential equation. It's ordinary because we're looking at a single function with regards to one dependent variable. X is a function of time. You could have, and you will have in the future, dc dx, or dc dt equals d squared dc dx squared. So concentration, for example, is a function of distance and time. So that would be a partial differential equation. And this is an ordered differential equation, and it is the second order because we have the second derivative. Soon you're going to be dealing with fourth order, fifth order derivatives, and you're going to be experts at that. We can also rearrange this expression and define what's called a natural frequency here and substitute this in our equation. So basically, what we'll be doing is dividing basically everything by m in this expression. And once we did that, actually you can see here, so we can say that, for example, omega is equal to square root of k over m, and we can just replace that here. So dividing out by m, rearranging, and we can define basically a natural frequency here. So when we do that, we can solve this ODE, and actually, I can show you how we can do that in Mathematica quite easily. So we can do it both ways. So for example, we can say m, I can say dsolve. Dsolve is a differential solver. I'm going to put my equation, so m times x second derivative with respect to t, plus k times x with respect to t. Set this equal to 0, and then I'm going to have to try to remember the syntax, but I think it is my equation x of t with respect to t. And when I do that, I'm going to clear my mass. When I do that, you see I have the following expression, which looks exactly like this expression here, except the sines and cosines are flipped, but that's arbitrary. So when we solve this expression, we have basically a function of our displacement of x as a function of time, and it's basically sinusoidal. This is an example of simple harmonic motion. And when you have simple harmonic motion, this basically form repeats, and it repeats over a period. So I define a period as from here to here, where my signal's repeating. So this is my t, which is my period. And it's defined as the time that it takes for my signal to repeat. I can define my period from here to here, and it'll be the exact same. I can take my period, and I could then basically calculate my frequency. My cyclical frequency is 1 over my period. And my omega, my circular frequency, equals 2 pi f. So we can use these relationships to confirm and find what is the natural frequency of this